In this video, we'll be looking at the multiple choice questions from AQA Chemistry Paper 1, code number 7404, from the year 2016. Right, the first MCQ question, question 10. Which element is in the D block of the periodic table? Now you will have a copy of the periodic table in your exams, so I've pasted it over here for easy reference. The way we can categorize the S, D, and the P block elements, we can do it in this manner. And the S blocks belong to these two groups. Alright, this is the S block. The P block is on this side. Right, these are our P block elements. And then the D block will be those that are found in between. Alright, D block. So let us look at our four options and then match them to the correct location. Selenium. Selenium atomic number is 34. Right, this is selenium. So selenium is a P block element. Antimony, atomic number 51. Right, also belonging to the P block. Tantalum, over here. Right, tantalum is the element that we are looking for, the D block. And just to confirm, looking at lead, right, lead is over here. Lead belongs to the P block. So question 10, our answer is C. +11. Which species contain an element with an oxidation state of +4? Right, so let's look at the first one. The unknown will be nitrogen, right? And oxygen, unless it is in the peroxides, oxygen usually will be assigned an oxidation number of -2. So letting the unknown hydrogen be X, we have 2 oxygen. So it's 2 times of -2, and then we equate the sum of the oxidation number to the charge. In this case it is +1. So solving the equation, the oxidation number of nitrogen is +5. Right, that's not what we want. Chlorine will be assigned X. We have 3 oxygen, each one is -2, and then the sum of the oxidation numbers will be equal to -1. So solving for X again, chlorine in this compound is +5. Sulfurous acid, assigning X to the sulfur. Right, each hydrogen is +1, so 2 times +1 plus X, 3 oxygen, and there's no overall charge, so the sum of the oxidation number is 0. And then we have an equation solving for X, X being +4. So C is our answer. Right, checking. Or option D, phosphorus will be X, and each chlorine atom is -1. The sum is equal to 0 because there's no charge. Right, phosphorus here is +5. So our answer is C. Number 12. 392 moles of pure gold in a bar measuring 10 centimeters by 40 centimeters. What is the density in kilograms per dm cube? So a good habit would be to convert the mass into kilograms, convert the volume into dm before we find the density. Right. So here's how we do it. Let's find out the mass of 392 moles of gold. So mass will be number of moles multiplied by the relative molecular or relative atomic mass of gold. If you refer to the periodic table, you will get 197. Then using our calculator, we will find that it is 77224 grams. And converting it to kilograms, because we want it in terms to be in terms of kilograms, right? 77224 grams will be divided by 1000. This will be the mass of 392 moles of gold. Now let's convert the measurements of centimeters to decimeter. Right. 10 centimeters is actually 1 decimeter. 10 centimeters is 1 decimeter. And 40 centimeters is 4 decimeter. So volume is equals to 1 multiplied by 1 multiplied by 4. So we will have our volume in terms of dm cube. Finally, we have kilograms, we have decimeter cube. We can actually find our density. Putting our kilograms and then our volume. Right, notice that it is now the units that we want, kilograms over dm cube. And then using our calculator, again we will find that the density is 19.3 kilograms per cubic decimeter. That will be option B. Number 13. Ions of two isotopes of iron are a nucleon number 53 and 56. So first thing to take note of is, for them to be the same element, for them to be iron, they must have 26 protons. So let's look at the options. The ions of both isotopes have the electronic configuration, so on. So first of all, let's look at the atom itself. It has 26 electrons, so the configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. Right, so this is the electronic configuration of the iron atom. For the ion, it must lose 2 electrons, and you'll be losing 2 electrons from the 4s shell. So this is the configuration for the iron ion, right, which does not fulfill what was written in option A. Right, option A, it seems that it's actually writing down the configuration for the iron atom. The ions of both the isotopes contain 26 neutrons. To find the neutrons, we have to take the mass number, the nucleon number, subtract it with the proton number. So 53 minus 26, we have 27 neutrons. 56 minus 26, we have 30 neutrons. So it is not true that both of them contains 26 neutrons. Option C, one isotope has fewer protons than the other. Right, that cannot be true. They are the same element. We expect them to have the same number of protons. So that leaves us with option D. They have the same kinetic energy. Fe56 will move more slowly than Fe53. So let's see why this is true. The kinetic energy is actually half multiplied by the mass multiplied by the square of the velocity. So if they have the same kinetic energy, it means that we can actually have an equation that looks like this. Right, where the masses and the velocity, the subscript refers to the isotopes. Now, since this is a smaller mass compared to this one, for them to be equal, the velocity for the one on the left side should be larger than the velocity for the larger isotope. Right, because this has a smaller mass, this is a larger mass. So for the equation to still be equal, we will need the velocity of the one with the smaller mass to be larger than the other isotope. So Fe56 will move more slowly than Fe53. Right, Fe56 will have a smaller velocity than Fe53. Successive ionization energy for element X. So the thing that we have to look out for will be where there is a big jump in the ionization energy. So we notice that from after removing the third electron, to remove a fourth electron requires a relatively large jump in ionization energy. It means that the first three electrons belong to the same outer shell, and the fourth electron could most likely come from an inner shell. Right, so it also means that this unknown atom comes from a group 3. So with that in mind, nitrogen is out. Nitrogen is from group 5. Phosphorus is also out. We are left with aluminium and boron. Both of them are from group 3. Right, so why is it boron, or why is it aluminium and not boron? Right, boron, if you check the periodic table, boron only has 5 electrons. Right, and then this graph shows that we are able to remove at least 8 electrons from the element. So it cannot be boron, which has only 5 electrons that can be removed. So it is aluminium. Right? Aluminium, for that matter, has 13 electrons. Which of these decreases down group 2? Right, as we go down group 2, so let's try to imagine the shells. Focusing only on the outer shell, we have 2 electrons on the outer shell. As we go down group 2, the electron is further away from the nucleus. Right, it is the protons in the nucleus that is holding the electrons back. So it is easier for the electrons to be lost as we go down the group. Right, because the attraction force from the outer electrons to the nucleus is weaker as we go down the group due to the distance So it is easier to lose the electrons as we go down the group. The ionization energy gets decreased. Right, the higher the ionization energy, it means that the more difficult it is to lose that first electron. Let's look at the other options that are wrong. Atomic radius. The atomic radius, because we are adding one more shell, the atomic radius should be increasing down the group. The number of protons should increase, right, as the proton number gets larger. Reactivity with water, right, the reactivity depends on the ability or the tendency to lose electrons, and then we have already discussed that it is easier to lose electrons as we go down the group. It will be easier, or the elements further down the group is more reactive. Right, so only the ionization energy decreases down the group. (16) Balancing and unbalanced equation. So what we can do, right, we can find out the number for the coefficient for sulfuric acid. So we try to balance sulfur. On the right side we have 3 and 1, so we have 4 sulfur on the right side. To make the sulfur to be 4 on this side, there are no other places with sulfur except at the sulfuric acid. We have to include a coefficient of 4. Right, once that's done, we can find out the coefficient for water. Let's balance the hydrogen. For the reactants side, we have 6, 8, so total of 14 hydrogen. There are no other places with hydrogen except for water, so we need to have 14 hydrogen here. It's already H2, so we need to include the coefficient 7. Right, so it is 4:7. (17) We'll be using the same equation again to find out the reducing agent in this reaction. The reducing agent, right, itself is being oxidized. In other words, its oxidation number will be increasing, oxidation state. So let's look at the few possibilities we have. H plus, option A. H plus, the oxidation number is +1. Right, we do not multiply by 2 here. Right, we are talking about each individual H plus. So it's +1 here. Let's compare to the hydrogen on the other side. Right, it's over here. The oxidation number of each hydrogen here is also +1. So it is neither a reducing nor oxidizing agent. Right, there's no change. C2O42-, right, the one in question will be the carbon. So let's find out the oxidation number of carbon. Assigning each carbon to be X, we have 2X because there are 2 carbons here. Right, each oxygen is -2, so we have -8, and then summing it up we will have -2, right, based on the overall charge. So working the equation, the oxidation number of each oxygen is +3, right, over here. And then let's look at what happens to the carbon on the other side. Right, the carbon on this side, oxygen is -4, so the carbon on this side, the oxidation number for carbon in carbon dioxide is +4. Right, so we can see that this compound has been oxidized, right? The carbon in here was +3, it has increased to +4, the oxidation number. Since it itself is being oxidized, it is a reducing agent. Let's check the other options that are wrong. K plus, right? K plus is here. Each one is +1, and the K plus that we find on this side, right? It is also a +1. Dichromate. Dichromate, you can memorize it to be +6. It's a very popular chemical. If you can't memorize it, we can do a calculation. Again, we assign each chromate to be X. 2 of them to be 2 X's. And then oxygen, each one is -2. 7 of them will be -14. And then we equate it to 2 -2. So, in other words, each chromate ion is +6. Let me use a different color. Chromate ion here, each one is +6. If you to check here, you can see that one way we can do it is we can check the charges of the chromate. This is SO4, 2-, sulfate ion. And then this means that the chromate is actually Cr3+. So, chromate was +6, it has decreased to +3, so the chromate was actually being reduced. In other words, the dichromate is an oxidizing agent. Now, you do not have these diagrams in your paper, right? I've searched for it and put them here just for easy reference. You have to find out which substance is a macromolecule. So copper itself is a giant metallic structure, so it's a metal, not a covalent structure, so that's out. Silicon dioxide, right? I found a picture here. Silicon dioxide is the macromolecule, right? It is joined together by covalent bonds between the silicon and oxygen atoms, and it is a large repeating structure. So this is the macromolecule we are looking for. P4O10, I found a picture here. P4O10, it is a covalent compound, but it is not a macromolecule, it is a simple molecular structure. Right, it's not so extensive as compared to silicon dioxide. And then magnesium oxide, this is an ionic compound. Number 19, a pale brown mixture of NO2 and N2O4 is allowed to reach equilibrium. Now, there's a mixture, a pale brown is essentially because one of the molecule is brown and one of the molecule is colorless, and we have to use the information that follows to figure out which one is brown and which one is colorless. So, when a plunger is pushed further into the syringe, the pressure increases and the mixture becomes paler in color. So now for a reversible reaction in equilibrium, when we increase the pressure, right, by pushing the plunger in, for example, the system will react by trying to release the pressure, or we have a lower pressure, and to do that they will actually shift to the side that has less gaseous molecule. Right, this is the change we introduced. and this is the response of the system. So it will shift to the side that has less gaseous molecule. In other words, it will shift to the right side, because here we have 2 moles of gas, and on the right side we have 1 mole of gas. So increasing the pressure, it will shift to the direction that has less moles of gas. And when that happens, the color change, they will be paler in color. It means that the molecule on the right side is colorless, and the molecule on the left side, the NO2, it is brown. Right? That's why when more of the NO2 becomes N2O4, the mixture becomes paler. So we have figured out the respective colors of the molecule here. Second information, when the syringe is placed in a hot oven, right, the mixture becomes darker. Placing in the hot oven is essentially raising the temperature, so temperature increases. When the temperature increases, the system will shift to the side that, and the direction will be the endothermic direction, right? Because it wants to remove the added heat. So we are told that the mixture becomes darker in color. In other words, increasing the temperature is favoring the backward reaction, because we know that we need to form more brown molecules. We want the mixture to be darker. So from there, we know that this direction is the endothermic in nature. Right, because increasing the temperature causes more brown molecules to be formed, which is the backward reaction. And we know that increasing the temperature favors the endothermic direction. So let's put all this information together. NO2 is brown. Right, so A and B are possible. C and D saying that NO2 is colorless, that is wrong. And then let's check the directions of the enthalpy changes. Right, forward reaction is exothermic. We have already established that the backward reaction is endothermic, so the forward reaction should be exothermic. Number 20, which molecule has the largest dipole? So let us figure out the number of lone pairs of electrons, bond pairs, and of course the molecular geometry of the molecules. So first off, we have ClF3. Let's draw the single bond for between the fluorine and the chlorine. Right, and then we know that chlorine has 7 outer electrons. It has used three of them to form 3 single bonds. So there are 4 unused electrons, 4 unbonded electrons. 4 electrons will form 2 lone pairs. So we have 3 bond pairs, 2 lone pairs. The molecular geometry will be a T shape. I found a diagram that illustrates the 3D structure. ClF3. So we have the 3 single bonds here. The lone pairs will be here. The 2 lone pairs here and here. Right, so and looking at the shape, we have the molecular geometry to be T-shape. Now, fluorine is much more electronegative than chlorine. These two fluorine, almost vertical to each other. These two fluorine, the dipoles can be considered to cancel each other out. Right, whereas for the fluorine on this side, there will be no other bonds to cancel out the dipole moment, so we have an overall dipole moment for this molecule. So the answer for molecule, we know that A will have a dipole moment. We might not be sure whether it has the largest dipole moment or not. So let's keep that in mind and check the other options. For B, BF3, boron. Boron has 3 outer electrons and it forms 3 bonds with fluorine. So there's 0 lone pairs and 3 bond pairs. And that will give us a trigonal planar shape. Right, trigonal planar, they're 120 degrees to each other, the bond angle. So they will be able to cancel each other. The dipole moments will cancel each other out. There will be no resultant dipole moment. Option C, sulfur hexafluoride. So sulfur is in group 6 and 6 of its electrons are involved in bonding to form 6 single bonds with fluorine. So in this case, it doesn't have any unbonded electrons. It will be 0 lone pairs and 6 bond pairs. Right, so we will have the dipole moments also cancelling each other out over here. Okay, let me choose a different color. You can visualize it as these two fluorine will cancel each other out for the dipole moments. The 2 fluorines on the red bonds will be cancelling each other out, and then the fluorine above and below will cancel each other out. Right, and I forgot to mention this is the octahedral molecular geometry. It's symmetrical. There will be no overall dipole moment. And CF4, CF4, like your CH4 methane and all that, is tetrahedral in shape. It's symmetrical. So although the bonds are polar, there will be no overall dipole moment because they will be cancelling each other out also. So CF4 also do not have any dipole moment. So eventually we end up with ClF3, the only molecule among the 4 of them with a dipole moment. Right, which is this molecule at the bottom here. A molecule of hydrocarbon, it means it only contains carbon and hydrogen, right? The fraction by mass of carbon is 9/11. Well, for convenience, let's just assign the carbon to be 11 grams because the fraction is over 11. And then let's do a quick empirical formula. So in terms of mass, grams, For every 11 grams, we will have 9 grams of carbon, and the rest will be hydrogen, 2 grams of hydrogen. And then let's convert them to moles. Mass over the relative atomic mass. Carbon is 12, hydrogen is 1. We will have the number of moles. And then let's figure out what are our numbers here. Find the simplest ratio. This we will have 0.75 and 2. Right. As much as possible, we try to have whole numbers as a ratio. So by observation, if I multiply this by 4, I will get a whole number. 0.75 times 4 will be 3. And for this side, I have to also multiply by 4, giving us 8. So in other words, for every 3 carbons, we will have 8 hydrogen. So that's the empirical formula for this hydrocarbon. We have xenon mixed with fluorine, right, forming another gas, xenon fluoride. So how do we account for all the volumes of the respective gases? Again, we will try to use a table to keep track. So xenon, fluorine, xenon fluoride, and it so happens that the ratio will be the ratio of the moles and the volumes will be 1:1:1, right, based on the Balanced equation. So initial volume, the change in volume, and then the final volume. Let's find out the respective numbers. Initially we have 30 with 20, and then none of the xenon fluoride is formed yet. So 0 for xenon fluoride. And by observation, we know that 1 volume of xenon will react with 1 volume of fluorine. So we can see that the fluorine is the limiting reagent here. The xenon is actually in excess. So all of the fluorine will be used up. So we use up all 20 of the fluorine. When 20 cubic centimeter of fluorine is used up, by ratio we will also have 20 cubic centimeter of xenon being used up. Like we say, 1:1 will react. And when 20 cubic centimeter of fluorine is used up, 20 cubic centimeter of xenon fluoride will be formed. So the change is formation of 20, so plus 20. And then let's do a tally to find out the final volumes. We had 30 for xenon, we used up 20, we ended up with 10 cubic centimeter left over. The fluorine, not surprisingly, because it's limiting reactant, there will be none left over. And the xenon fluoride, we form 20. So adding up the volumes, final volume will be 10 plus 20, we have a total volume of 30 cubic centimeter. Which of the following solutions will react with exactly 0.5 moles of sulfuric acid? Right. All these solutions in the options are alkaline, so it's an acid-alkali reaction. So let's look at two possible scenarios: reacting with potassium hydroxide and reacting with barium hydroxide, because the ratio of the moles are different. So for potassium hydroxide, we form potassium sulfate and water, and we know that we need 2 moles of potassium for every 1 mole of sulfuric acid. Right, this is crucial to know the ratio of the moles. For barium hydroxide, and sulfuric acid, we form barium sulfate and water. Right. The ratio between them will be 1:1. So, looking back at the question, if we had 0.05 moles of sulfuric acid, right, if potassium hydroxide was used, we will actually need 0.05 multiplied by 2 moles of potassium hydroxide. So 0.1 moles of potassium hydroxide is required. For barium hydroxide, to react with 0.05 moles of sulfuric acid, we will need the same moles, right? Ratio 1:1, 0.5 moles of barium hydroxide. So once we establish this, we will just need to check which of the conditions or which of the options fulfill either potassium hydroxide or barium hydroxide. So we have the volumes here and then the concentration, keeping in mind to multiply or to convert the volume into dm³. So for the first one, we have 50/1000 multiplied by concentration, which is 1. So the first one only gives us 0.05 moles of potassium hydroxide. Right, we need 0.1, so this is incorrect. The second one, 100/1000 multiplied by 2, it gives us 0.2 moles of potassium hydroxide. Again, not what we want. We want 0.1. So A and B are incorrect. Right, going down the list, the third one, which we got 0.2 moles of barium hydroxide. So not what we required. The final one, right, 50/1000 multiplied by 1. The last option supplies us with 0.5 or 0.05 moles of barium hydroxide, right, which is the number of moles that we require. Question 24. We have two equations, and then we are given the idea, or we are told that we started off with 2 moles of sodium azide, and then we have to find out the amount of nitrogen molecules that will be formed. So starting off, we have 2 moles of sodium azide, right, from here. So from 2 moles of sodium azide, we form 2 moles of sodium and 3 moles of nitrogen. Right, so this is one source of nitrogen from the first equation, and then we know that the sodium here will actually form more nitrogen gases, right, from the second equation. So from these 2 moles of sodium that we got, we put it inside this equation. 2 moles of sodium, and we'll find out how many extra hydrogen we will have. So 10 will give us 1 mole. 2 moles will give us 0.2 moles of nitrogen. Right, these 2 moles of sodium comes from here, in case you're wondering. So what is the total amount of nitrogen formed? We have 3 moles here from the first reaction, and then we have a further 0.2 moles from the subsequent reaction. So in total, we have 3.2 moles of nitrogen molecules. And then to convert the moles into an Avogadro's number, right, because this is essentially Avogadro's number, 3.2 multiplied by 6.002 or 6.022 10 to the power 23. Right, and inputting into our calculator, we have 1.93.